In the previous video in this series, I covered an explanation as to why gravity or acceleration due to gravity on or near the Earth's surface can be considered constant and be treated as a force that causes a constant acceleration of 9.8 meters per second squared. Once we understand that it causes a constant acceleration, we can begin to explore relationships between the influence of this acceleration on the distance that objects travel over different time periods and the speed or velocity at which they're traveling. So to look at these relationships, let's introduce some concepts. First is velocity, which is the distance traveled over a time interval. It's described by the equation velocity equals d distance over time, t, and in the metric system has the units meters per second. Acceleration is change in velocity over time, sometimes written as delta v, change in velocity over time. Since velocity is meters per second, and we're looking at the change in velocity over time, it has the units of meters per second squared, which is meters per second per second. So these are the equations or the variables needed to explore the influence of objects moving under the influence of gravity. And the thing to keep in mind again and again is in these situations, we're looking at a situation where acceleration is caused by gravity and it is constant. While acceleration is constant, all these other variables change. So with a constant acceleration of 9.8 meters per second squared, we can start figuring out the behavior of an object. In this case, a ball at time 0. It's being held up in the air, so it's got a velocity of 0 at time 0. If it's let go, it will begin to fall, and after 1 second, it will be traveling at 9.8 meters per second. After 2 seconds, it will continue to accelerate 9.8 meters per second every second. And so after 2 seconds, it'll have twice the velocity. It'll have a velocity of 19.6 meters per second. And after we can keep doing this, after 10 seconds, it'll be traveling 10 times as fast. In this case, it'll have a velocity of 98 meters per second. Again, the special case where no other forces are acting on it, in this case, most notably, air resistance. The thing to keep in mind is this is change in velocity. We are not talking about how far an object has traveled. We have to do something else to figure out distance. Right now, all we're looking at is a constant acceleration, which is change in velocity. If we multiply the acceleration times the time it's traveled, we can figure out how fast the object is traveling at any given time. Another thing to think about is that this force can cause a lot of acceleration. 98 meters per second squared, which is the velocity that can be achieved, or 98 meters per second, which is the velocity that can be achieved in only 10 seconds, is very fast. It's over 350 kilometers an hour, or in English units, over 200 miles an hour. Let's back up again and look at calculating distance traveled. And to do this, we need to do some manipulations because we don't know how far things traveled. What this constant acceleration allows us to figure out velocity at any given time, but over any period of time, velocity is always changing. So how do we find distance traveled, given that velocity is always changing? The way we do this is to think about what the average velocity is. This only works when acceleration is constant. But if acceleration is constant, the average velocity is always going to equal the velocity at the beginning of a time interval plus the velocity at the end of that time interval divided by 2. And in the special case where we have velocity of 0 at the beginning of the time interval, this simplifies down to the velocity at the end of the time interval divided by 2. So in each of the cases illustrated in this figure, after 1 second we know the final velocity, divide that by 2, we get the average velocity over that 1 second. And we can do this for each of these intervals. Just divide the velocity at the end of the interval, divided by 2 will give us average velocity. Once we have average velocity, we can calculate distance using the equation velocity equals distance over time. So in this case, if we look at the distance traveled from time 0 to time 1, the average velocity is this final velocity of 98 meters per second, divided by 2, 4.9 meters per second. Take this equation, average velocity equals distance over time. Time is 1 second, so we can put 4.9 meters per second in for velocity, 1 in for second, and we simply solve for distance. In this case, we can figure out that the ball will have traveled 4.9 meters in 1 second. We can do this for all the other relationships. If we let it travel for 2 seconds, the final velocity is 19.6. If we put it through this equation, we'll find that it will have traveled 19.6 meters. And after 10 seconds, the final velocity will be 98 meters per second squared. The final velocity will be 98 meters per second, and the ball will have traveled almost 500 meters. So this shows how we can go from average velocity to distance traveled and calculate all these relationships, but there is an easier way by combining these equations, and this is what I want to walk through quickly. And the trick to this is the fact that all these relationships are able to be linked through average velocity. When we make these assumptions that we always have to keep in mind, we're talking about a situation where gravity is causing the acceleration, so it's constant, and the velocity at time 0 is 0. We saw that if we know average velocity, we can figure out distance and time, because average velocity equals distance over time. And we also know that the average velocity in the special case where velocity at time 0 is 0 is the final velocity divided by 2. Remember, we calculated those final velocities by multiplying the acceleration times the time, so final velocity equals acceleration times time. We do a couple of substitutions. First, we take final velocity out of, we replace acceleration times time for final velocity. We get average velocity equals acceleration times time divided by 2. And if we combine all of these through average velocity, we can see that distance over time equals acceleration times time divided by 2. And again, with the simplifying assumptions of velocity at time 0 is 0 and constant acceleration, we can calculate, we can rearrange this equation to find different things. If we know how far an object has traveled and how long it's taken, we can solve for acceleration and estimate the acceleration due to gravity, which is the point of this exercise. But we can also rearrange it in a couple different ways. We can calculate distance if we know acceleration and how long an object has fallen for. And we can also tell time with gravity. So we know how far an object has fallen. We know the acceleration is 9.8 meters per second squared. And so 2 times the distance divided by acceleration, take the square root of that, will give us the time. So now to wrap this up, let's just use an example of estimating acceleration due to gravity with a ball and a stopwatch and some kind of way to measure distance. So in this case, we have a ball that's 11 meters above the ground at time 0. We let go of that ball and time how long it takes to fall, and we find that it takes about 1.5 seconds to fall 11 meters. We can now plug that into the equation where we put 11 meters in for distance, 1.5 seconds for time. Find that if we solve this equation, that its acceleration due to gravity is estimated to be about 9.78, or round up to 9.8 meters per second squared. Keep in mind that this is a sort of contrived example. In real life, if you tried to do this, it would be very difficult to precisely measure that 1.5 seconds, but you'll get some estimate somewhere around 10 meters per second for acceleration due to gravity. The more carefully you can measure time, the more accurate your measurement will be.